My name is MaliaKency. I will be discussing what perfect and non-perfect randomness is. Perfect randomness is the uniformly distributed bits independent of any other existing data. Perfect randomness is the concept of absolute unpredictability of a stochastic process. This generates unbiased and completely independent results. Is it truly perfect? This is subjective in that we may not always be able to truly determine whether a process is perfect random or not, as there may be unavoidable bias introduced. We can only measure and evaluate outputs of various sources of randomness to understand that a source or process that generated output of the source is sufficiently random for the needs of some applications. So in general, a source of perfect randomness must be able to produce any possible result with a uniform probability, and therefore we can say that a source of perfect randomness must produce a uniform distribution. So a stochastic process that outputs a uniform distribution should have maximized entropy, a metric that quantifies the unpredictability of a distribution. The most fundamental construct of modeling a source of perfect randomness is a machine that generates n bits in the set of 0 to 1 to the power of n, where each bit has an independent and uniform probability equal to p. Random statistical sampling is a common way to avoid bias in deductions. Sample space is usually taken as small as possible. It is crucial to cover homogeneously different parameters of the underlying set with a few instances as possible. Even many parameters aren't easily accessible, which in fact disallows proper selecting of best sample space. However, perfect randomness is used in proven to overcome this complication. It also helps to choose sample space for the simulation that brings the best results. Some efficient perfect randomness generators. Random numbers can be generated from random macroscopic events such as rolling dice or flipping a coin. The best way to think about perfect randomness in this sense is an arbitrarily long sequence of coin tosses, where each coin is fair, meaning having a 50-50 chance of landing on heads or tails, and each toss is independent of all others. This will result in having the same probability. Also, truly random numbers can be generated more efficiently by sampling random fluctuations in nature, such as measuring the electric current of TV static over time. So what is non-perfect randomness? Non-perfect randomness is defined as non-uniform random processes, only partially independent of other data. It is a property of any natural phenomena that exhibits some degree of unpredictability, though that behavior may not be entirely random and that may exhibit veracity. A source of non-perfect randomness is generally considered to contain some degree of perfect randomness. So therefore, a source of non-perfect randomness can generally be thought of as a source of randomness that can be observed to satisfy some minimum entropy measurement. Because perfect randomness is expected by most of the applications, it is natural to attempt to post-process weak randomness into nearly perfect randomness, which can be substantially used in algorithms and protocols. This process is called randomness extractors. The goal of randomness extraction is to take samples from a weak random source, one where samples may not be uniformly distributed, but do have some inherent randomness, and generate samples that are close to being uniformly distributed. Randomness extractors are algorithms that, when given one sample from a weak random source, produce a sequence of truly random bits. These extractors are algorithms that gain random bits from these widely studied types of weak sources. Their construction depends on the source which that are based on. We can divide weak sources of randomness into two classes: extractable and non-extractable sources. From extractable sources, one can obtain by a deterministic procedure, nearly perfect randomness. Various examples of non-trivial extractable sources do exist, but most natural sources, such as defined by entropy of allowed distributions, are non-extractable. In such cases, non-deterministic randomness extractors have to be used. Some types of weak randomness sources. First one is Santa Vazirani. Second one is von Neumann sources, which is defined as a sequence of binary independent random variables with fixed but unknown biases. The last one is min entropy, which is used to measure the amount of random bits that can be extracted from a source. The development of these models of randomness sources can be traced back to von Neumann presenting a model of such a source based on independent tosses of a biased coin with arbitrary but constant bits. Then Santa Vazirani, or also called SV source, brought the impossibility of the perfect random bits extraction. Every bit depends on all previously output bits. Because delta is always greater than 0, every string of bits appears with probability higher than 0. The cancelling of this condition led to the notion of min entropy sources, with the only condition that the min entropy of such a source is upper bounded.